How to save energy in pump performance and control. This is part 2 of 2 in continuation of our earlier video of same topic. In this video, we will cover how we are losing energy in throttling and how it can be saved by reducing diameter of impeller, means trimming of impeller, as well as by adopting other measures such as variable speed drive, reducing speed of the pump, and we can see the effects of these measures in power saving. Energy loss in throttling. If we are operating a pump by throttling a discharge valve, then we are losing lot of energy. So how we can save energy? By operating a pump with full open of discharge valve by matching our flow requirements and save power in our pump operation. So I will give you an example. Consider a case where we need to pump 68 meter cube per hour of water at 47 meter head. This is a 47 meter head and these are the pumps A to E, which characteristics curve are shown. This is our 68 meter cube per hour flow requirement. If we select pump E, this, where it will give us 47 meter head, and at best efficiency point 60% efficiency, it will provide us 68 meter cube this flow. So the hydraulic power will be calculated 68 by 3600 into 47 into 1000 into 9.81 upon 1000 equal to 8.7 kilowatt, means shaft power equal to 8.7 upon 0.60. 60% is our pump efficiency, so power will be work out to 14.5 kilowatt. If we calculate motor power, then 14.5 upon 0.90 means 90% of motor efficiency is considered. Then we will work out 16.1 kilowatt power for motor operating a pump at 68 meter cube per hour flow requirement and at 47 meter head. Similarly, if we select pump A, we are throttling discharge valve. The pump efficiency is 50% and our flow requirement is same, 68 meter cube per hour. So now you see the pump characteristics curve A, where we will get the same flow 68 meter cube per hour, but head will be 76 meter and pump will operate at 50% efficiency. So we will calculate hydraulic power Q meter cube per second into total head into G meter square per second upon 1000. So it will be work out 14 kilowatt. The shaft power will be calculated 14 upon 0.50, considering 50% of pump efficiency, then it will be 28 kilowatt. And if we will calculate motor power, then it will be 28 upon 0.90, considering 90% of motor efficiency, it will be works out to 31 kilowatt. Means if we operate the pump by throttling, we will have a energy loss of 31 minus 16.1 kilowatt equal to 14.9 kilowatt. So this is an example how we are losing lot of energy in pump operation by throttling a discharge valve. Effect of speed variation. You can see a picture of a head flow curve where different RPMs of a pump are given. As we know, impeller peripheral velocity is directly proportional to shaft rotational speed for a fixed impeller diameter. So varying the shaft rotational speed has a direct effect on the pump performance. The equation relating rotodynamic pump performance parameters of flow, head and power absorbed to speed N are known as affinity laws. As we know, flow Q is proportional to N, head h is proportional to n square, power p is proportional to n cube. For example, if RPM is reduced to 90%, the flow rate reduced to 90%, head reduces to 81% and power reduces to 72.9%. So, the speed of a pump play a very important role in increasing or reducing the flow and head and power requirements. Effect of impeller diameter change. You can see a graph between head, flow and power. So all HQ characteristics curve are shown where different diameter impellers characteristics curves are plotted against head and flow, and similarly with respect to power requirement. Changing the impeller diameter gives a proportional change in peripheral velocity. It follows that there are equations similar to affinity laws for the variation of performance with impeller diameter d. Flow Q is proportional to d, head h is proportional to d square, power p is proportional to dq. For example, if diameter is trimmed by 10%, flow rate reduces by 10%, head reduces by 19%, power reduces by 27.1%. So here you can see in this picture that this is a curve for 400 mm dia impeller. This is 373 mm dia impeller and this is 326 mm dia impeller. So we can see here if impeller diameters are changed, this head and flow will accordingly change. Similarly, you can see the power requirements are changed with respect to these impeller diameters. If impeller diameters are reduced, power requirements are reduced as stated in the affinity laws. Efficiency varies when the diameter is changed within a particular casing. This relationship shown here apply to the cases for changing only the diameter of an impeller within a fixed casing geometry, which is a common practice for making small permanent adjustments to the performance of a centrifugal pump. Diameter changes are generally limited to reducing the diameter to about 75% of the maximum, head reduction to about 50%. Beyond this, efficiency and NPSH are badly affected. Speed changes can be used over a wide range without seriously reducing efficiency. If your pump impeller diameters are changed, they can affect pump efficiency also. So here you can see in this picture where these diameters are changed of the pump and efficiencies are also accordingly changing. Impeller diameter changes are done in a particular permissible limits. Beyond this, they can affect NPSH and efficiency. Performance control. For example, reducing the speed by 50% typically result in a reduction of efficiency by 1 to 2%. The reason for the small loss of efficiency with the lower speed is the mechanical losses in seal and bearing, which generally represent less than 5% of the total power, are proportional to speed rather than the speed cubed. It should be noted that if the change in diameter is more than about 5%, the accuracy of the squared and cubic relationship can fall off, and for precise calculations, the pump manufacturer's performance curve should be referred to. Certain high flow, low head pump have performance curve shape somewhat different and have a reduced operating regions of flow. This requires additional care in matching the pump to the system when changing speed and diameter. Cavitation. Liquid entering the impeller eye turns and is split into separate streams by the leading edges of the impeller vanes, an action which locally drops the pressure below that in the inlet pipe to the pump. If the incoming liquid is at a pressure with insufficient margin above its vapor pressure, then vapor cavities or bubbles appear along the impeller vents just behind the inlet edge. This phenomenon known as cavitation has three undesirable effects. The collapsing cavitation bubbles can erode the vane surface, especially when the pumping water-based liquids. Noise and vibrations are very high and increased with possible short-end seal and bearing life. The cavity areas will initially partially choke the impeller passes and reduce the pump performance. In extreme cases, total loss of pump developed head occurs. Pump suction performance (NPSH). The value by which the pressure in the pump suction exceeds the liquid vapor pressure is expressed as a head of liquid and referred to as a net positive suction head available (NPSHA). This is characteristics of the system design. The value of NPSH needed at the pump suction to prevent the pump from cavitating is known as NPSH required (NPSH-R). This is a characteristics of the pump design which is given by the pump manufacturer. The three undesirable effects of cavitation described above begin at different values of NPSH available, and generally there will be a cavitation erosion before there is a noticeable loss of pump head. However, for a consistent approach, manufacturers and industry standards usually define the onset of cavitation as the value of NPSH-R when there is a head drop of 3% compared with the head with cavitation-free performance. At this point, cavitation is present and prolonged operation at this point will usually lead to damage. It is usually therefore to apply a margin by which NPSH available should exceed NPSH-R. So in all the cases, the NPSH available should be more than NPSH required to avoid cavitation in any manner. As would be expected, the NPSH-R increases as the flow through the pump increases. In addition, as flow increases in the suction pipe work, friction losses also increases, giving a lower NPSH available at the pump suction, both of which give a greater chance that cavitation will occur. NPSH-R also varies approximately with the square of speed in the same way as pump head, and conversions of NPSH-R from one speed to another can be made using the following equation. Q is proportional to N. NPSH-R required is proportional to N square. It should be noted, however, that at very low speed there is a minimum NPSH required plateau. NPSH-R does not tend to zero at zero speed. It is therefore essential to carefully consider NPSH in variable speed pumping. So when variable speed motors are used for pump operation, this NPSH must be carefully considered. NPSH available shall be always designed pump installed in such a manner that NPSH available shall always remain more than NPSH required at all the speeds. Thanks for watching the video. If you like this video, hit like button below, share it with your friends and colleagues, subscribe our channel for getting updates on upcoming videos. Please leave any comments, feedback to improve the videos. Thank you.